Dear world, welcome back to Trace representation. So in today's video, we'll be studying the Trace representation. So what we can see in the diagram, this is actually called pictorial representation. That means a representation for our visual and understanding purpose. But in programming, we cannot represent the tree like this. So either we have to represent it utilizing an array. As I have already made the point that today we'll be understanding the representation of an array, then using linked list, then using graphs, and then stack, and then queue. So first see how we can represent it in an array. So array is that type of structure when you represent this entire pictorial representation, this representation. So you represent the entire tree in array like structure, like this. In linked list, if we represent the same things, we represent it in terms of tree node. We call it tree node, and we represent the tree node like this by creating our own tree node. So that is the representation utilizing linked list. If we represented the same things utilizing graph, then we utilize, in case of graph, we use nodes, and the nodes are expressed in two terms. These are called vertex and edges. These are called vertex and edges. And when you represent the same thing in stack is also required in a tree for representing the in-order, pre-order, post-order, etc. type of traversal. We utilize a stack. So stack has a general architecture like this, and that is how we represent the stack. And when we represent the tree, this tree using the stack, we either entirely push the tree node, that is the root, entirely comes there, and this way we utilize, and that have a structure like this sometimes, or like this tree node. So it depends what we want to actually insert inside it. After this, we will be also utilizing the queue for us. We'll be utilizing the queue, that how we can represent. So we represent through queue also for sometimes like level order traversal. If you are performing level order traversal, then we utilize this queuing. So these are why we use various type of representation. So we'll be observing all one by one. So let's move to the tree structure. So this is the tree structure I have already represented. So we can call it a array type of representation. So let's observe how we can represent this. So to represent this one, we actually make array. This is how array is represented. Array looks like. So how many elements there are? There are total 7 elements. So let's make it index. So in computer programming, we always start everything from 0. So 0, 1, 2, 3, 4, 5, 6, 7. We don't require 7 because up to 6 we have already made 7. So if we insert the same elements level by level, so this is called zeroth level. That is zeroth level that I've already made you understand in the first video. So at zeroth level we'll be inserting 1. At this first level we'll be starting 2 and 3. We are inserting from left to right. And now try to understand, why are we inserting from left to right? Which type of representation is this from left to right? This is the architecture of complete binary tree, feature of complete binary tree. That means right now we are discussing for complete binary tree. That means if we get any tree, first we have to convert that tree into complete binary tree. So the formulas that I am gonna write are written here. Those are all applicable for complete binary tree. So let me write, these are applicable for complete binary tree. Here we are mainly talking about complete binary tree. And as you can see, this one is already a complete binary tree. The representation is like this: 1, 2, 3, and then 4, 5, 6, 7. This is filled from left to right side, and when any tree is filled from left to right side completely, that is called complete binary tree. So that is complete binary tree. Now at the second level, this was zeroth level, this was first level, and this is second level. So at the second level we'll be inserting 4, 5, 6, 7. So this is the array representation, how we can represent it. So to find that what will be, from here we try to find the correlations. That if we have found the parent, what will be the index of child? So to find the formula I have already written, that child will be at the index 2 is to I plus 1. So let's try to find the child of 0. First we'll be trying to find the child for this index for 1. So index of 1, left child of root, left child of node 1 which is also the root. Here this 1, this is also called the root, that is also called the root. So now we'll be try to find the left child, the index of 2 in our array. So the formula as says 2 star I plus 1, 2 star I plus 1. So if we just substitute the value of 2 star I, so 2 into the value of I is what? The value of I is 0. So we'll be just substituting 0 plus 1. So we get the position 1. That means the left child 2 will be inserted at position 1. And now if you observe from here, this is at index position 1. So we got it. Now we'll be applying the formula to find the right child, this one. How we can find this right child. So okay, let's again apply the formula for right child. Right child of node 1. We are finding the right child of root node 1. So that is 2 star I plus 2. So if you apply the 2 star I, that is 2 into 0 plus 2. That means we get at index 2. So the formula here, that left child will be stored at index 2 star I plus 1. We got it. The right child will be stored at index 2 star I plus 2. Always 2 star I plus 2. And only when we are utilizing a complete binary tree. So if we get any binary tree, first we'll be converting that into complete binary tree. First we'll be converting tree any tree whatever we get into complete binary tree. Complete binary tree into complete binary tree. Okay, now the parent, suppose we have to find the parent of 7. We want to find the parent of this element 7. So this is 7 and the parent of 7 is 3. The parent of 7 is 3, that is called parent. So we want to find the index, so we'll be finding that one. Left parent of node 7, parent of node 7. So the parent of node 7 will be according to the formula I minus 1 by 2. So while we apply the formula, we'll be taking the floor value. So after from floor value we get the in 7. So 7, this is at the index 6. This is at the index 6. Look, that is the index 6. So we'll be substituting 6 minus 1 by 2. And we will be taking floor value. So 6 minus 1, that is 5. 5 by 2, it comes to be 2. That means it should be at position 2. The 3 should be. So if you notice, the 3 is already in the position 2. This is at the position 2. So this is how we can get the positions of the tree representation in the array structure from all those formulas. So we always have to keep in mind those three important formulas. That root is always stored at index 0. At index 0, root is always stored at index 0. And then left child is stored at index 2 star I plus 1, and right child is stored at index 2 star I plus 2. 2 star I plus 2. And parent of any index is I minus 1 by 2. It is stored at I minus 1 by 2. The formula is I minus 1 by 2, and we have to take the floor value of it. So I made a recap of this, and this is how we represent the entire tree in tree structure. So suppose let's take another example. We're taking another example of any tree. Let's call it 1, 2, 3, and here is 5. So can I represent it like this? The question might arise in your mind that can I represent it like this? This is the array structure 1, 2, 3, 4. Okay. So the index 0, 1, 2, 3, 4, 5. The point, one thing is to remember, that we will always take the index starting from the street value 0, because we are programmers. So we always have to take the value starting from 0. So look, if we just substitute level by level. So for 0th level, first we'll be inserting 1, then at this level we'll be inserting 2, 3, and 4 we'll be inserting 5. Will it give us the correct value? So the question, so it will not give us the correct value. It will never give us the correct value. Let's see if it provides the correct value. So the index, we are trying, this is 5. 5 is at third index. So let's try to find the parent node position. So parent index parent index of 5 is, and we apply the formula I minus 1, I minus 1 by 2. So the I value is 5 and 5 minus 1 by 2. So we get the position 2 here. So somehow actually got the position of 5 to be true, but it not works. Okay, let's take another example. Now let's try to find the position of root from here. So let's make it more longer to understand it better. We add more elements with this 5, and here we add 6 and 7. So now as for level by level, we'll be inserting 6 and 7. So now our 6. Now if we want to 5 with respect to 6, we'll be trying to find the parent with respect to 6. Then parent of 6. Parent of 6. The parent of 6. So we'll be again applying the formula mod of I minus 1 by 2. So the position of 6, that is 4. So we insert 4 minus 1 by 2. We'll take the modulus value 4 minus 1, that is 3 by 2. The modulus will be that is equals to 1.5. So we'll be taking the floor value, that is 1. So we'll be trying to find the parent of 6, that is 5 at one position. But look, at one position there is 2, and the 5 is at third position. The 5 is at third position. So this is where, so that is what, okay, so that is where it fails. Our formula fails here, and we have to find the reason that why our formula fails. We got the value to be 1 here, we got the value to be 1 here as per the formula we provided, and here the parent of 6, the parent of 6, 5 is stored at index 3. This is third index, and our formula tells it should be at one position. So this is where it fails, and the problem is this is not a complete binary tree. That is not a complete binary tree, not a complete binary tree. This is not a complete binary tree. So first we have to convert this one 2 3 4 5 6 7 into a complete binary tree, and then it will work. So let's try to understand. The example was, first we had 1 as a root node, and then 2 3 we had the child node 2 3 of 1, and 3 had the child node 5, and 5 had the child node 6 and 7. 6 and 7. So that is, so first we have to convert the complete binary tree, and to complete the complete binary tree, that means it should have two child nodes at wall, and this should be at the wall level, and it should be filled from left to right side. So it is not having the child nodes, we'll be adding child nodes 0 0. It's not having child nodes, we'll be adding child nodes 0 0. This is also not having child nodes 0 0. Okay, now all the nodes are having child nodes. So if we insert them in elements, now now we will be representing them in an array structure. Now this is our array representation of this tree, array representation of the tree. So let's insert it. There are a lot of elements, so let me make the room. 0 1 2 3 4 5 6 7 8 9 10. So it starts with 0 1 2 3 4 5 6 7 8 9 10 11. So first we'll be substituting the value as we insert by level. So for zeroth level we'll be inserting 1. For the first level we'll be inserting 2 and 3, 2 and 3. Then we'll be inserting those. Now notice after 2 3 these are null, so we'll be just inserting null. Okay, now there is 5. Again at that level there is 4 null, and 6 and 7. So this dash represents null here, that is null. Here the dash representing null, null. This is null, that means there is nothing, that is void. So now if we try to find the child, in that case we try to find the parent of 6 which was at location 3. Now we notice this representation. Here the parent, okay, from a long time we are struggling in the same example. Actually I also tried researching that what the problem was going on. So the problem figured out that we actually work with complete binary tree, and this tree that I have used in this program is not a complete binary tree. This is not a complete binary tree. Not a complete binary tree. This is not a complete binary tree, and that's why we got the problem. So first we have to take we have to understand the criteria. We always have to keep the criteria of complete binary into mind. So the first criteria is wall levels will be filled one by one. So let's erase it. Okay, the first criteria is wall levels should be filled level by level. All nodes should be filled level by level, should be filled level by level. So that is the first criteria that we didn't follow here. Just observe. There is 2, 3 in our first level. 2, 3 in our first level. And there is, these are all empty. These all nodes are empty. And after that we have again taken the nodes empty. So we have empty nodes at 2 level. At 2 level we have empty nodes. Here also we have empty nodes. Here also we have empty nodes. So at these are the 2 levels we have empty nodes. But the complete binary tree criteria tells that we can have empty nodes. Empty nodes only at the last level. That means if that was our last level, okay, if that was our last level, then we could have also those empty nodes. So empty nodes we can only have empty nodes at the last level. We can have we can hardly have empty nodes. We can hardly have empty nodes at the last level. So this is the last level we can have nodes. And if we think with that respect, okay, now again if you construct the tree with that respect, so we will get to see that our program works. Again, let's check if it works or not. So first let's form the array. This is 0, 1, 2, 3, 4, 5, 6, 7, and we insert the elements 1, 2, 3, now null, 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 and this is 5. Okay, so now if you try to find the child, now if you try to find the parent of 5, parent of 5, parent of 5, parent of 5, then it will be simply the index of 5, that is 6 minus 1 by 2, and we'll be taking the floor value and it becomes 2. So now we got that it has matched our formula, and this parent 3 is already at the index 2. So this time our formula matches and we got it. That means our formula only works when it's a complete binary tree, and through the long struggle you all understood that it fails when we don't follow the property of complete binary tree. Okay, so till now we understood all about complete binary tree. Now we'll be understanding the tree representation using linked list, that how we represent the tree using linked list. Tree node 1, 2, tree node 2, tree node of 2, tree node of 3, then we represent this 5 as like this, tree node of 5. So this is how we represent in linked list. So what the architecture goes, now we will be converting this tree node into architecture. So while we utilize the linked list, we have the general architecture like this. First we have a left pointer for pointing towards right. This is left pointer that points toward the right, so this is left pointer. Now we have a right pointer that points towards the right. This is the right pointer that points toward the right. So this portion that goes for the right pointer, here our right pointer is stored, and here our left pointer is stored, left pointer. And here in the main section data is stored here. So the data, that is integer data, so we'll be storing the integer data 1 here. So that is the general structure. Now left, this pointer points to again another new node, and here at the data position this 2 is inserted, 2 is stored, 2. Again this right points to the right node, that is 3, so we simply insert 3. and again they keep on pointing. So this is the general structure and architecture through linked list, so that how we can represent the tree in linked list. We'll be understand the coding section in the next video. So this was the representation. Now we'll be understanding using graphs that how we can represent. So let me, okay. So I'm keeping it in that section. Now we'll be understanding that how we can represent it through using graph. So graph is what? Graph is simply tree, but when it's connected. When if we just connect the tree 1, 2, 3, this is the tree, and these are empty nodes and 5. And if we just somehow connect those trees like this, it becomes a graph. So that is called a graph. That a connected tree is called graph. So if we represent this, we'll be representing the vertices by the nodes. We'll represent the nodes 1, 2, 3 as vertices as we represented. That at vertices position, all the nodes are coming 1, 2, 3, 4. And edges. Edges is the edge. This we represent this edge, the position 1 to 3 is as the path. So there is 1 to 2. Sorry, this is 1 to 2. So we have represented this path like this 1 to 2. This path, this section has been represented as 1 to 3, 1 to 3. Now this one 3 to 5, we have represented the 3 to 5. This is 3 to 5, 3 to 5, sorry. And there is 2 to 4. So this is for another graph. And if we just take 4 here, so we will be representing the 2 to 4 like this. So this is how we represent the graph. Okay, now we'll be representing the tree. Stack. So using stack we can represent in two manner. First, using stack when we perform recursion. When we perform recursion, so we work in stack using two manner. First, sometime we perform recursion, and sometime we utilize for iteration. And these are the main two methods how we implement the entire tree, either using recursion and or using iteration. So recursion will always become easy for us. So what we do in the recursion, that we have a stack like this stack, and this is the stack. And in recursion, when the function calls, so let's call that we are calling a tree node, that is the tree node. So in recursion we call another tree node from inside this node. So we completely insert this tree node, we insert this nodes, the linked list node into this one. So this is stored inside our stack, that is stored inside our stack. One by one we keep inserting those through the recursion process. One by one we call the recursion and we insert inside this stack. So this is stack. We store here the nodes, the tree nodes, the tree nodes. Those are inserted into that section. But while we utilize the iteration, while we perform iteration, we completely store different things. That is the tree. Okay. So let's say this is the tree 1, 2, 3, 4, 5. So in iteration we completely perform different things. That if that is the stack, this is the stack here. So first we start from our current node. Let's say our current node points to 1, the root. This is the root one, root. So in iteration we entirely insert this root. That means we insert this current node pointer root into that. That means while we perform iteration we entirely insert the entire tree. That means this entire tree is inserted, entire tree gets inserted into this root section. Next one, again we utilize the second program line like this: current equals to current dot next, I mean current dot left, current dot left. So again our pointer, that pointer comes to this section and it inserts the two root node here. If we do like this, current equals to current dot right, so we insert the three nodes, entirely three nodes from here. So entire the architecture of 3 to 4 to 5 is stored in this memory. So we actually store the references, the current node, we pass this one into the stack architecture, and this is what we perform in the iteration architecture. We will be breaking down and observe the code how it matches with that. So this is the representation of stack. Now Kiwi that we use during level order traversal. Level order traversal, that is, suppose we have a tree 1, 2, 3, 4, 5, 6, and we want to insert the elements level by level, first 1, then 2, 3, 4, etc. For that we use kiwi, that type of structure, and we use elements in this kiwi. So this is where we insert the tree nodes in kiwi structure, and that is what I have written. The problem in array representation that it wastes spaces for sparse tree, and very fast access via index calculation. Second, the profit of linked list, that this is flexible and it is better for memory efficient. Even here the insertion order is maintained. We maintain the insertion order here. We also contain each pointer to its children, and it's also now graph. Graph is utilized for complex trees. Suppose we have complex trees, and for that we utilize the graph. And now the stack representation. Stack representation is used for in-order, pre-order, and post-order recursion. It is used for both recursion and iteration. And Kiwi, that is mainly used for level order traversal, that I've already told you. So in next video we'll be observing how we can implement it in coding section through codes, Java codes. So okay, meeting in the next session.